Dear students, we begin Unit 1 with the topic Mixture of Gases. The working fluids employed in most of the heat engines are not homogeneous gases but are mixture of gases such as air, combustion products, etc. Means in heat engines, when fluid is burnt, they produce gases. Those gases are not homogeneous gases but are mixture of different gases. For example, if petrol is burnt in an IC engine, that forms gases which work on the piston head to push the piston in the downward direction, thereby producing work. So those gases are the mixture of gases which may consist of different components of gases. These constituent gases present in the mixture are assumed to be ideal, means they will be following the ideal gas laws. They do not interact with one another chemically, and the gas mixture obeys the laws of ideal homogeneous gases. Same as an individual gas obeys all the gas laws such as Charles' law, Boyle's law, Gay-Lussac's law, it follows characteristic gas equation. Similarly, we presume that gas mixture which consists of these gases also obeys these laws. Each gas in the mixture behaves independently, means every gas has its own properties and accordingly it behaves independently. It occupies the entire volume of the mixture and exerts its own pressure on the walls of the container. Means pressure corresponding to that component will be exerted by that gas on the walls of the container, and overall pressure belongs to the pressure of the mixture. Now consider a homogeneous non-reacting mixture of ideal gases. Say this is a container of volume V. On the right side in the diagram you can see, which consists of say gases A, B, C. More number of gases may be there. We are considering these three gases at say temperature T and pressure P. Pressure P is measured with the help of a pressure gauge and temperature is measured with the help of a thermometer, and they are occupying volume V. Now every individual gas has certain number of moles which will not be equal, which will depend on the mass of individual gases. So let us presume that Na, Nb, Nc are the number of moles of individual gases in the mixture, and corresponding masses of these gases are Ma, Mb and Nc. Right? Now from the conservation of mass, you can say that total mass of the mixture will be sum of the individual masses of the components. So Ma plus Mb plus Mc will be equal to total mass of the mixture M. Similarly, number of moles of each constituent, if you sum up, it will give you the total number of moles available in the container. That is, total number of moles of the mixture will be equal to Na plus Nb plus Nc. Here it is showing B, it's not B, it's C. Right? Now, sigma m is equal to I is equal to 1 to k if number of components is k. K may be 1, k may be 2, k may be 3, k may be 4, or and so on. Then sigma I is equal to 1 to k mi is total mass. Similarly, total number of moles will be sigma I is equal to 1 to k ni, where k is the number of constituent gases in the mixture. Right? I hope it's clear. Now what is mass fraction? The mass fraction of each component of the mixture is defined at the ratio of the mass of the given component to the mass of the entire mixture. Very simple. Means if there are three components with masses Ma, Mb, Nc, then Ma upon total mass M is mass fraction of component A, Mb upon M is the mass fraction of component B, Mc upon M is mass fraction of component C, and so on. Right? So this is the equation M is equal to Ma plus Mb plus Mc from the last slide, and you divide both the sides by M, then 1 is equal to Ma upon M, Mb upon M, Mc upon M, and so on. Now just now we have said that Ma upon M is mass fraction of component A, Mb upon M mass fraction of component B. So these mass components are shown, mass fractions are shown with the help of X. So mass fraction of component A, Ma upon M will be Xa, Mb upon M, Xb, Mc upon M, Xc, and so on, right? So what does it mean? What this indicates? That means sum of the total mass fractions or sum of the mass fractions of each component will always be equal to unity or 1, right? So sum of the parts by mass or mass fractions of constituents in a mixture equals unity. Now when the analysis of gas mixture is made on the mass basis, it is called gravimetric analysis. Okay. Now come to mole fraction. In the similar manner, as you defined mass fraction, you can define mole fraction also. The mole fraction of each component of a mixture is defined as the ratio of the moles of each constituent gas to the total number of moles contained in the mixture. If number of moles पूरे mixture का अगर n है और Na, Nb, Nc ये सब individual constituent के number of moles हैं, then Na upon n will give you the mole fraction of constituent A or gas A. Nb upon n is equal to mole fraction of gas B, and so on. ठीक है ना? Now n is equal to Na plus Nb plus Nc divided by n, then 1 is equal to Na upon n, Nb upon n, Nc upon n, and so on. Now Na upon n, that is mole fraction, is shown by Y. So Na upon n, it is mole fraction of constituent A, so we call it Ya. Nb upon n, mole fraction of constituent B, we call it Yb, and so on. So what does it indicate? It indicates that the sum of the mole fractions of individual components in a mixture is always equal to 1. The sum of the parts by moles, that is mole fractions of constituents in a mixture, equals unity. Is it clear? I hope it's clear. While going through this, you should have a pen and notebook in your hand and just go on noting down so that you remember, right? You need not see again and again this video. Instead of that, just go on noting the important things. Then you will remember. Now we come to partial pressure and Dalton's law. Now consider a homogeneous non-reacting mixture of ideal gases A, B, C. Since we considered 3 components initially, we are continuing with that. We consider a homogeneous non-reacting mixture of ideal gases A, B, C. Let us say they are in volume V at temperature T and pressure P, occupying a volume V. Now, what will happen if we remove all the components from the mixture and only keep one component in the same volume? Then the pressure will be reduced, because initially when mixture was present in this volume, then the pressure that was exerted was corresponding to all the gases, or pressures exerted by individual gases, right? So if you remove 2 gases, only one gas remains, then whatever is the pressure will correspond to this gas, right? So we can call it PA. Similarly, if you remove A and C and only gas B is there in the same volume and same temperature T is maintained, then you can see pressure. So maintaining the same temperature and same volume, you can see the variation in pressure. So every time the pressure that you measure will be corresponding to that particular component of gas, right? So same volume is filled with individual components one by one at the same temperature, then the pressures, corresponding pressures will be the pressures corresponding to that particular component. So let it be presumed that each constituent of the mixture exists separately at temperature T and volume V. Pressures PA, PV, PC exerted by individual gases are measured separately, right? So individually, if you measure, let us say pressures are PA, PB, PC and so on. Now each of these pressures would be less than the total pressure of mixture, because some of these pressures is the mixture pressure. So naturally these pressures will be less than the mixture pressure. You are all aware that general gas equation or equations of state for ideal gas is represented by PV is equal to mRT. This can be applied to the gas mixture and also to the constituent gases. For example, for mixture you can write PV is equal to mRT, where P is the pressure of the mixture of gases filled in a container of volume V at temperature T. Then what is R and M? M is the mass of the mixture and R is the characteristic gas constant of that mixture. Now you have studied earlier in class 12th and also in first year that when number of moles of any gas are multiplied by its molecular mass, it gives you the total mass of the fluid. So M can be replaced by N into capital M, right? So M is replaced by Nm. So this equation becomes PV is equal to NMRT, right? Now for any gas, if you multiply its molecular mass with its characteristic gas constant, it gives you a unique value R mole or R0, which is called universal gas constant. And we have seen earlier in first year that its value always comes out to be 8314 joules per kg mole K, right? So for any gas, if its characteristic gas constant is multiplied by its molecular mass, it will give you the same value that you have already seen, right? So equation finally becomes for mixture PV is equal to nR0 T or R mole T, where T is the temperature, V is the volume, P is the pressure of the mixture and N number of moles of the mixture. R0 universal gas constant. Now for constituent gases A, B, C, which we considered earlier, you can write the similar equation. PAV is equal to NaR0T, since we considered earlier that in the same volume at same temperature, if one gas is filled, it will be applying pressure PA on the walls of the container. That PA is corresponding to the constituent gas A. So PAV is equal to NaR0T. Similarly, PBV is equal to NBR0T, where NB is number of moles of the gas B. Similarly, PCV is equal to NCR0T and so on. Right? Now, if you add for components all these equations left hand side and right hand side, PAV plus PBV plus PCV is equal to NaR0T plus NBR0T plus NCR0T. That is PA plus PB plus PC multiplied by V will be equal to Na plus Nb plus Nc into R0T, right? Now Na plus Nb plus Nc, this is the total number of moles, can be replaced by N. So this is equal to right hand side equal to NR0T. Now if you call this equation D and this as equation C, if you consider these two equations, from these two what you have, since right hand side is same, so left hand side PV is equal to PA plus PB plus PC multiplied by V. Therefore P will be equal to PA plus PB plus PC, right? That means P is equal to sigma Pi, where I is the component of gas, whether A, B or C and so on. So you can say that Pi is equal to NiR0T upon V. This represents the pressure of the component I that would exert if it acts alone, occupying volume V at temperature T, right? So this is called the partial pressure of the ith component of the gas mixture. So basically, what is partial pressure? Partial pressure of any gas is the pressure that the component would exert on the walls of the container if it is present alone in the same volume at the same temperature, right? So this is called partial pressure. So PA is equal to NaR0T upon V, PB is equal to NbR0T upon V. So what are the variables? P and N. For each gas, number of moles are substituted here, then it will give you the corresponding pressure of that gas. That is called partial pressure of that gas. So if you join or add all the partial pressures of the components of any mixture, that will give you the pressure of the mixture, right? So what I said is has been defined here. Partial pressure is defined as the pressure which individual component of a gas mixture would exert if it alone occupied the volume of the mixture at the same temperature. So from the equation, that is last equation, we can say that total pressure of a mixture of ideal gases is equal to the sum of the partial pressures of the individual gas components of the mixture. इसी को डाल्टन्स लॉ ऑफ पार्शियल प्रेशर्स कहते हैं. दिस इज नोन एज डाल्टन्स लॉ ऑफ पार्शियल प्रेशर्स. नाउ these are the relations that implicit in the Dalton's law. That means T is equal to TA is equal to TB is equal to TC. We have kept the temperature constant even when the single component occupying the same volume, we said at the same temperature. That means TA is equal to TB is equal to TC. Similarly, in the same volume we are putting it, so V is equal to VA is equal to VB is equal to VC. Now mass we have already discussed, Ma plus Mb plus Nc. So in terms of specific volume, V can be replaced by Mv, where M is the mass of the mixture, V is specific volume of the mixture. Similarly, capital Va can be replaced by Ma and lowercase va, that is MaVa, where Va is the specific volume of component A. Ma is the mass of the particular component, that is equal to MbVb, that is equal to McVc. So in this equation we have replaced capital V, that is total volume, by mass into specific volume, right? So combining these two equations, F and G, what we have, M upon Mv is equal to Ma upon MaVa, Mb upon MbVb, Mc upon McVc. Now from this equation, 1 upon V is equal to 1 upon Va plus 1 upon Vb plus 1 upon Vc, or 1 upon Va means inverse of specific volume, that is density. So rho is equal to rho A, rho B, rho C, where rho is the density of the mixture and rho A, rho B, rho C are corresponding densities of the gas constituents. I hope it's clear to all. In the next lecture, we shall discuss Amagat-Leduc law of partial volumes. That is, partial or reduced volume of a gas component represents the volume that this gas component would occupy if its temperature and pressure were equal to these parameters of the gas mixture. What does it mean? In the previous case, we have discussed that if the gas component alone is working in the same volume at the same temperature, then the pressure exerted on the walls of the container corresponds to the partial pressure of that particular component. Now, if that gas component is kept at the same temperature and pressure, then the volume that it will occupy will be corresponding to that particular component, and that volume will be called partial or reduced volume of a gas component, right? And this relates to the Amagat-Leduc law of partial volumes. So we shall discuss this law in detail in the next lecture. Also, we'll see the relation between partial pressure, mole fraction and volume fraction, and we shall also find out the expression for gas constant, molecular mass, enthalpy, entropy and specific heats for gas mixture. And also we shall discuss another law, that is Gibbs-Dalton's law, and we'll see how is it different than the Dalton's law of partial pressures, right? So till then, goodbye, good luck.